Morning, guys. Hope you guys had nice weekends. Um, my main objective for today is to talk about thermal conductivity, and in doing so, we should round out all the Chapter 11 content. There's going to be two more formulas to look at involving the rate at which thermal energy conducts through various materials. If we do manage to get through all of that today, then rather than start anything new tomorrow, I think we'll take the chance for tomorrow to be questions, free work on homework day, so that you can work on Chapter 11 stuff or previous Chapter 10 stuff too, if you want to round that out. And I'll, as usual, be in here answering questions for our class time. And then if that goes smoothly and you guys are comfortable with the Chapter 11 assignments after working on them tomorrow, then on Wednesday we'll probably begin Chapter 12, which will be about the laws of thermodynamics. And that'll additionally take about a week, and then we'll be done with the heat and thermo part, and we'll start moving towards Test 1. Let me know how that sounds, if there's any complaints or objections at this particular time. Additionally, let me know if you guys have any questions or things you'd like to talk about before I get into the thermal conductivity notes today. I want to make sure to address any concerns that you may have had over the weekend. If anything comes up while we're going today, please let me know. Please stop me mid-sentence. And I'm going to remind you to do that every single time we meet. It's just a habit of mine, and I'm sure my students get annoyed by it. Okay. If there's no present questions or objections, then we'll continue looking through our material. Let me make sure everything is set up. All right. So, brief, quick review. Last time we were looking at phase change. So just quick review. In order for something to change phase, you have to either introduce enough thermal energy to complete the phase change based on its mass and based on that material's latent heat, or you must remove that amount of thermal energy if the phase change is moving in the colder direction. We looked at some sample questions involving that math, some complete phase changes from various states into others. Let me know. There are questions about this on the homework. Again, as you're working on that, let me know what issues you encounter. The last part of what is labeled as Chapter 12 is thermal conductivity. And we've used the word thermal conduction before. It's specifically the method of heat transfer where two objects are touching and thermal energy can just transfer between those two objects via the direct contact. It's the most straightforward one. It's the one we're going to focus on the most. The other two types are convection and radiation. Convection happens in a pot of boiling water, and radiation is when energy is radiated outwards as electromagnetic radiation, including light and infrared and gamma rays and all that good stuff. Now, there's a current image on screen that I want to focus on for just a second because it represents, in a way, both radiation but also the thermal conductivity math that we're going to begin looking at. This is a house, and this is specifically an infrared image of a house. Now, infrared is one of the types of electromagnetic radiation. It's on the EM spectrum, which we'll talk more about that near the end of the summer, but every single type of electromagnetic radiation is on the spectrum. They're all basically cousins, and the spectrum goes from radio, micro, infrared, visible light, UV, X-ray, gamma ray. They're all the same type of thing. And so currently this image was taken by an infrared camera that can detect the infrared radiation coming out of this particular house. And we've noticed in the past, scientists have noted in the past, that when objects have a lot of thermal energy, they tend to radiate more infrared radiation than normal. This is how night vision goggles tend to work, or I guess thermal vision goggles more specifically. Those goggles, the human eye can't see infrared radiation, but we've invented these machines that can detect it and can form an image based on the infrared that it absorbs. It's basically light, it's just the human eye can't see it. And the brighter something looks on an infrared camera, the more infrared radiation it's giving off. So that means that the particular parts of this image currently on screen that are bright, namely the brightest things are definitely the windows of this house, are giving off more energy because they have more energy in the first place. Well, that's one of the explanations. If something looks brighter on infrared, it's one reason is because it just has more thermal energy to begin with. More thermal energy something has, the more infrared radiation it just naturally gives off. That is true of the human body as well. Since humans are constantly making our own thermal energy, then we show up pretty easily on thermal vision cameras because we tend to be warmer than our surroundings because we make thermal energy and most inanimate objects don't. But there's an aspect of conduction that I want to talk about in relation to this particular image as well. For this specific picture, the bright spots are giving off a lot of infrared. They are giving off more thermal energy. And the dark spots, like the sky and the roof and even the snow, are giving off less radiation. They're giving out less thermal energy. And that's not just a function of how much energy they're radiating, it's also a function of how much energy is currently allowed to conduct out of those different materials. Because if you think about it, all of the exterior pieces of this house are touching the same temperature air. They're all exposed to the same temperature winter. This is a winter picture. There's snow on the ground and snow on the roof. They're all exposed to the same temperatures, and so all of the paneling, all the roof materials, most of the surrounding area should all be the same temperature. And yet, all these different pieces are showing up with different intensities on this thermal vision camera. So the explanation for that isn't just that their temperatures are different, because they're all reasonably the same for the most part. The explanation here is that the different parts of this building and the surroundings all have different rates of thermal conductivity. Humans show up pretty good on thermal vision because we're constantly making our own thermal energy. Your body's literally a furnace. You feed it food and it turns it into heat to keep you alive, among other things. This house is pretty similar. It's got heaters and maybe a fireplace inside making thermal energy, and the point of the walls of the house is to keep that thermal energy on the inside where it warms up humans and protects you from the winter. But inevitably, because, the warm air inside the house is touching the walls of the house, and the walls of the house are touching the cold air on the outside of the house, there's going to be thermal conduction through the walls. So, the bright spots and the dark spots on this image don't just represent which parts of the house radiate more, it also represents which parts of this house allow more thermal energy to pass through them, because they have higher rates of thermal conductivity. If you think about, your dwelling on I know it's currently the dead of summer, but think about, just for a minute, imagine the middle of winter. You're nice and cozy inside, and it's freezing outside. I guess that also doesn't happen much in the South, but hypothetically, you're warm and cozy inside your dwelling, and it's really frigid cold outside, middle of the night, middle of winter. If you were to walk around and touch the walls of your house, they'd feel at about the same temperature as everything else inside. But then imagine you touch the glass of your windows. I'd say, on average, on a cold winter day, the windows are probably the coldest part of your house. And that's because the windows, because they're very thin and made out of glass, conduct the most thermal energy through them out of the materials that make up your house. Looking at this particular picture here, the windows are all white hot. They are constantly spitting out energy into the surroundings. And the energy that they're releasing that's showing up on the camera is coming from inside the house. Thermal energy from inside the house is traveling through the window and out into the cold, and then it shows up on the thermal camera. Those windows have the highest rate of thermal conduction. They're allowing the most thermal energy out of them and into the cold. Meanwhile, the walls of the house, your walls are designed to keep thermal energy in. They're thicker. They've got insulation in the walls. They're made out of wood, which doesn't conduct thermal energy super great. They conduct less heat. They keep more heat in your house. So they don't look as bright on this picture because less thermal energy is coming out of them. They're designed to keep more thermal energy in, whereas your windows are designed for you to be able to see through them. They're not great at keeping heat in because they're thin and made out of glass. And then the darkest part of the house is easily the roof. And in most houses, the roof is designed to be one of the most well-insulated parts of the building because it's constantly dealing with the beating heat of summer and the fact that in winter, heat is going to try to rise out of the attic, and you want to try to mitigate that. So your roof is usually the most well-insulated part of the building. And that's why it's currently the darkest thing on the picture, in addition to the sky, which is too far away to picture. So the different intensities on this one image are due to different rates of thermal conductivity. Oops. So, heat always flows from hot to cold. That's why thermal energy is moving from inside the house into outside the house. Or vice versa, on a summer day, if you want the inside of your house cold and the outside of the house is very hot, thermal energy will move from outside the house to inside the house. It always flows from hot to cold. But, and the rate at which thermal energy flows depends not only on the temperature difference. We've talked briefly about the fact that if you touch something hot and it feels hot to the touch, if it feels really hot, that means that the temperature difference between it and your hand is greater and more thermal energy is flowing into your hand more quickly. That speed of energy transfer is the rate of thermal conductivity. The faster the energy flows, the more energy is conducting per unit of time, the higher the rate of conduction. So whenever you touch something and it feels like a more intense sensation of temperature, like you touch something that recently had boiling water in it, that feels very hot. Or if you submerge your hand in ice water, that's going to feel really cold because that's a pretty big difference between your temperature and the temperature of what you're touching. The temperature difference does affect the rate of thermal conductivity, but other properties of the object also affect the rate of thermal conductivity as well, not just the temperature difference between the two things that are touching. I want you to think briefly to when you woke up this morning. Usually, after you go to bed, everything in your house, your room is still for the night. Lights are turned off, barely anything's moving, it's dark, it's calm. And all the objects in your room are touching the same temperature air. They're all touching each other. So over the night, your room should reach thermal equilibrium. Everything in your room should be at pretty much the same temperature as each other when you wake up in the morning because there's been no energy introduced into the room. There's been nothing moving around to shuffle energy around. So everything in your room should be the same temperature when you wake up. So you wake up, you get out of bed, and as you start touching things around your house, Your bed sheets or your carpeted floor, they all feel pretty warm, pretty neutral. Touching them is no real shock to your senses. But if you touch something that's made out of like metal or maybe a hardwood or linoleum floor, that tends to feel colder than the surroundings. So, like, say you wake up, you're cozy in your bed, all your sheets feel warm, but then you get out of bed, your feet touch the hard floor, and all of a sudden, ouch, cold. This was especially true when I was a student at PC because I spent 3 out of 4 years in Georgia dorm, and at the time, it may still be, I don't know. The floors were for the most part just stone granite. So waking up in the morning, getting out of bed, not only was the floor physically uncomfortable to stand on just because it was hard, it was also really cold. So that was never very fun. But the thing is, so the floor feels cold, the metal stuff in your room feels cold, but objectively, all the objects in the room should still be the same temperature for the reasons I already stated. They have been touching each other all night. They've been thermally interacting all night. They've been exposed to the same temperature air. They should be the same temperature, and yet they feel like they're different temperatures. Remember how I mentioned that the human body does not have a built-in thermostat? You can't detect an object's temperature by touching it. What you detect is the rate at which thermal energy exits you or enters you. You can't touch something and say, yes, this is exactly 50 Celsius. No, you just detect the rate of thermal conductivity. And certain materials conduct heat in and out of them better than others. The metal objects in your room, the cold stone or linoleum floor, they all have higher rates of thermal conductivity. Those materials allow heat to move through them very quickly, which not only means that heat can move from one end of the object to the other very fast, it also means that they suck heat out of you faster than other objects. So if you touch a cold object that has a high rate of thermal conductivity, it's going to feel like the temperature, like the sensation you get when you touch it is just going to feel more intense, even if it's at the same temperature as another object you're touching. I've been trying to get you to remember things right now, but even objects around you right now, you can try to demonstrate or simulate that fact. If you touch, say, like the fabric of a nearby chair or sofa and compare it to the sensation of touching something nearby that's made out of metal. I have some coins on my desk, and I also have, lots of paper on my desk. And the metal coins feel colder than the paper does, even though they should be the same temperature. Again, same air, they've been touching the same desk all night, they should be the same temperature. And they are the same temperature. They are actually the same temperature. What feels different is the rate at which the objects take thermal energy out of you based on what they're made out of. That's why some things just feel more intense, more cold, or more warm than other things. Even if they're the same temperature, they can feel different because of what they're made of. I'm hoping that the examples I'm giving and the things I'm saying make sense based on things that you've experienced in the past. This is when I talk about this phenomenon, this is one of those things that a lot of people have experienced, but they might not have ever consciously noticed. Like, it's just something you're subconsciously used to and you might not think about that often. So maybe accidentally you might spend the rest of my secret hope is that you'll spend the rest of the day thinking about this whenever you touch something and it feels, colder than the objects around it when it probably shouldn't. Actually, I think the coldest thing on my desk is currently the metal of my production microphone. It's the coldest thing I've currently got. at my desk right now. Whereas the warmest thing is hands down my whirring computer desktop. So, I've been hand waving a lot of this so far, and now we're going to start putting some numbers to these phenomena, as we tend to do in physics class. Now, there's currently a lot on the screen. I'm going to tell you what things are important, namely, if you're, say, writing things down for the sake of your notes, or if you're going over these slides to copy down or look over a formula sheet. The one formula on the bottom here, P equals Ka Th minus Tc over L, is the important one that you want to make note of right now, the one that you'd actually want for your notes. The parts above it are just elaboration, which I will go over in a second. But if you're looking for a formula to put in your notes, it's this bottom one here, P equals Ka Th minus Tc over L. And I will explain all the terms in that formula. So, rate of thermal conductivity. It's the rate of energy flow. Again, if you touch something cold, thermal energy is going to transfer out of you and into it. The colder the object feels, the more thermal energy is transferring out of you per unit time. It's literally just happening faster. And that means that you're measuring energy, Q, per unit time. So Q divided by delta T. Now, energy over time is something we've already measured, or something that you would have already measured in a previous physics class. Energy divided by time is the same as the rate at which work is being done. If you remember the physics concept of work, you're using energy to accomplish a task, like you're lifting something, and you would have used formulas to figure out how much energy it takes to lift a certain object. If you do work in a certain amount of time, you're using energy over time. And a previous formula, a previous concept, already describes and defines that phenomenon. That is the concept of power. Power is defined as the rate of energy use or the rate of energy change over time. And so, we're actually bringing back an old variable to describe thermal conduction rather than giving you a completely new one. Power, capital letter P, measured in watts, is the variable and the unit for thermal conductivity because it's just energy flow. It's still joules per second. 1 joule per second is still 1 watt. So power, thermal power, is the rate of thermal conductivity. And in some of your questions on the homework and on the test that we'll eventually take and on the quiz as well, you might be asked to calculate thermal power. That's just a synonym for the rate of thermal conductivity. They're synonyms, they'll mean the same thing. I might use them interchangeably. Assignments will use them interchangeably. So that might be one thing to make sure you've got written in your notes with a little asterisk next to it. Thermal conduction, the rate of thermal conduction is the same thing as the rate of thermal power. It's something to keep in mind when looking over questions. So, P, thermal power, is the rate of thermal conduction. And we have some formulas to help us examine what variables affect the rate of thermal conduction. I'm going to focus on the bottom formula here. So, power, thermal power, the energy flowing into or out of an object, is equal to, there's a lot of variables here, and I'm going to list them in order of relevance, or rather in the order, I'm going to list them one at a time, but maybe not in the order they're written. P equals, the rate of thermal conduction for an object is equal to, first thing I'm going to focus on is this open parentheses, Th minus Tc, close parentheses. This represents the different temperatures on either side of an object. So imagine, I'm going to tab back over to the slide with the house on it real fast. Whoops. Look back at the house picture real quick. There's a lot of thermal energy inside the house. The air inside the house is at a higher temperature than the air on the outside of the house. So there's a pretty big temperature gradient difference between those two spaces. And those spaces are separated by the walls of the house. So if, for example, the inside of your house is at a nice and cozy 80 degrees Fahrenheit, which is a temperature that someone might set their thermostat to in winter, and the outside of the house is like, 30 Fahrenheit, less than freezing, that's a difference of 50 degrees Fahrenheit across those two spaces. And that difference is across the gradient that is the wall of the house. So there's as far as the wall is concerned, the walls of the building, on one side of the wall is 80 degree Fahrenheit air, outside the wall is 30 degree Fahrenheit air. So that's a difference of temperatures across the wall of about 50 Fahrenheit. That is what the TH minus TC term in the formula represents. It's the temperature difference across the object that you're looking at. So if we were, say, trying to find the rate of heat flow through the walls of that house, we would need to plug in the two temperatures on either side of that wall. If the hot side of the wall is 80 Fahrenheit and the cold side of the wall is 30 Fahrenheit, then we would plug in 80 minus 30, and that would be a temperature difference of 50. The reason this is in the formula is because the bigger the temperature difference, the faster the thermal energy will flow. Again, the hotter something is when you touch it, the more thermal energy you'll get through contact with it, and the bigger, the more intense the sensation that you measure with your hand will be. So, the temperature difference across the object matters for the rate at which thermal energy will flow. This additionally means that if, say, the two temperatures on either side of the wall were the same, say it was just a normal spring day and the house was 75 Fahrenheit inside and 75 Fahrenheit outside, then there's no temperature difference across the wall. And then there's going to be no heat flow through the wall, because heat always flows from hot to cold. If everything is the same temperature, there's no heat flow. So in this formula, if the hot temperature and the cold temperature were the same, you'd get a heat flow of 0 for that reason. So a TH minus TC term represents the difference in temperature across the object that you're examining. Now for the other terms in this formula. Next one I want to look at is the A term. This represents the surface area of the object in question. I'm going to hold up a little pad of sticky notes to help with this one. Let's imagine that this object is the wall of a house. So, one side of the wall, let's just keep using a winter day as an example. One side of the wall is hot, one side of the wall is cold. And the surface area of the wall, the flat, square amount of area that is able to be touching the air on either side, affects the rate at which thermal energy can move through it. So, if this was a pretty big wall of a pretty big house, this big square would maybe be something like, 10 by 10, maybe 10 by 20 feet. And every single square inch of that area is space that air molecules can collide with and send thermal energy through to the other side. So the bigger your wall is, the faster thermal energy can flow through it, because that wall is able to touch more air at once. Think of it, I would compare it to the size of a door. The physically larger a door is, the more people, the more stuff you can fit through it more quickly. The bigger the door is, the more things are just going to be able to flow through it every second. It's the same thing here. the physically bigger, the bigger the area of an object, the physically more air is able to touch it, and therefore that increased amount of air is able to physically transfer more thermal energy into that surface more quickly. Let me know how that feels to you so far as I've explained it. Checking to make sure I haven't lost signal. So, the bigger the object, the more physical contact it's able to have with whatever it's touching. So the A term in this formula represents the surface area of contact between two things. If I was to try to make another example real quick, let's say that I take my cup of cold water here. There's ice cold water in here, so it feels cold to the touch. If I was to touch this whole cup with the entire flat of my hand, that's some measurable amount of flat 2D surface area that I could calculate. I could find the flat surface area of my hand. And if I'm using my whole hand to grab the cup, if every single square inch of my palm and my fingers is in contact with it, then there's a certain amount of thermal energy that will flow out of my hand and into the cold cup. But if I, instead of touching the cup with my whole palm, if I just touch it with one fingertip, the surface area of my one fingertip is a lot less than the surface area of my entire hand. And so even though I'm still touching the same object, and even though it's still the same temperature difference, there's still going to be less total thermal energy flowing out of my entire hand because there's less surface area for it to come out of. It will take longer for all of the energy in my hand to flow out of it and through my finger, because it just takes longer for it to fit through the reduced surface area of my fingertip. As opposed to if I use my whole hand, energy is able to come out of my hand more quickly because there's more space, there's more literal area for it to come out of. So that's what the A term represents. It's going to be the surface area of transference. The area here, it's best to use meters squared for this. So say you're, again, looking at the thermal energy flow through a wall, you'd want to find its surface area, multiplying its width in meters times its height in meters. The next term I want to look at is the L term. This represents the length of the object, or rather the distance through the wall that the thermal energy needs to flow. So if I was using a wall as an example, the L term represents how thick the wall is. If the wall is physically thicker from one side to the other, then that's more object, that's more distance that the thermal energy has to travel to get from the hot side to the cold side. Excuse me. Imagine hypothetically the walls of your house, and say that you, again, we're going to keep using that cold winter day as an analogy, or as an example, excuse me. And if you touch one wall of your house that's made out of that's somehow 10 feet thick of wood, compared to touching a different part of your house that's just 1 inch of wood thick. Again, we're talking about the thickness of the wall here, not its surface area, not its width or height, but how thick it is. The thicker the wall, the longer it takes thermal energy to try to worm its way through from one side to the other. It physically takes more time to get through. It's literally like having to walk a longer road. The longer the pathway, the physically longer the pathway, the more time it takes to traverse it. And so that's what the L term represents. It's how long, how thick is the object that thermal energy is trying to transfer through. For some other miscellaneous examples, the metal that forms like pots and pans tends to be pretty thin because the point of a pot and a pan for cooking is that you want thermal energy to transfer through it. You want heat to come from the heating element up through the pan and into your food. So those objects tend to be made out of pretty thin metal for that material, whereas the walls of your house, something that you don't want thermal energy to move through, tend to be a lot thicker. You have better insulation that way. Similarly, coolers. If you own a cooler or if you've used one at any point, the thicker its walls are, the easier it is to keep the objects inside cold. Because there's just physically more material, more distance that the heat has to travel through. So, L term represents the distance the heat has to travel. It's the thickness. And it too should also be measured in meters. Keep that in mind. The last variable present in this formula that affects rate of thermal energy flow is this K term. This represents the thermal conductivity constant of the material in question. So pretty much every specific formula that we've talked about so far this term has some weird specific constant in it that depends on the material in question. This is continuing that particular trend. So lowercase k refers to this table of thermal conductivities. So every different material has a different rate of thermal conduction. Here we have various metals which have relatively high rates of thermal conduction, all things considered. This represents the amount of energy that is able to pass through that material every second. So, highest one currently on this table is silver. 427 joules of thermal energy are able to flow through silver every 1 second. Whereas, if we look at these bottom two parts of the table, the gases and the nonmetals have very, very low rates of thermal conductivity. The gases especially are the lowest presently on this table. I think the lowest one here is, I think we have a tie between air and nitrogen, which makes sense since air is mostly nitrogen. Thermal energy tends to transfer very poorly through nonmetals and through gases, but especially through air in this particular case. Less energy flows through it per second. And if you think about it, you're constantly touching air. And at room temperature, you don't really notice it because thermal energy transfers through it so slowly. You only really notice the temperature of the air when it's very different to the temperature of your own body. You only start getting uncomfortable when there's about a 10 or so degree difference between the air's temperature and what humans tend to be comfortable at, because heat just transfers so poorly through air. Air is a surprisingly good insulator, and that's actually why I mentioned that windows tend to be pretty bad insulation. Like the glass of the windows is pretty bad at keeping thermal energy from moving through it, which is why on a hot day the windows feel pretty hot, and on a cold day the windows feel pretty cold. Certain windows that have better insulative properties than others, rather than being a single pane of glass, are actually two separate panes of glass with an air gap between them. If you take two panes of air with a layer, if you take two panes of glass and keep a layer of air between them, that has better insulation than just a single pane of glass of the same thickness, since air conducts heat a lot worse than glass does. Glass still isn't that strong of a conductor, but air conducts even worse, frankly, which makes worse conduction means better insulator. I think I'm stumbling over my words a little, sorry. So, All the numbers on this particular table refer to the K constants here in this formula. You never have to memorize any of them. You will have access to this table or the numbers in this table as you need them. You can refer to these notes whenever you need to. Alternatively, most of the homework questions should tell you the numbers if you need them. And some trends to note are that metals conduct heat very well, so they have higher numbers. Non-metals tend to conduct heat very poorly, so they have much lower numbers. This is actually directly correlated to how well the object in question conducts electricity. Usually, metals conduct electricity pretty well, whereas, air and non-metals conduct electricity pretty poorly. So thermal conduction and electrical conduction go hand in hand. They, like the materials that tend to conduct one very well, will also conduct the other very well. So, those are all the various factors that can affect the rate of thermal energy flow through an object. What it's made of, its surface area, how thick it is, and the difference of temperatures from one side to the other. They all affect the speed at which energy flows through it. And so that's all of the various parts of this particular formula. I feel like that was a lot of talking. My lungs are actually kind of tired. So, please stop me. Please interrupt me. Any questions, comments, needs, concerns, etc. I'd like to make sure that we use this formula at least once today. Start applying it. So, as a quick sample, I mentioned the thin walls of cookware, of metal pots and pans, so let's use one of those as an example. How much power will a copper-bottomed pot transfer to ice-cold water while it is on top of a stove eye at 300 degrees Celsius? The pot is 12 centimeters in diameter and is 2 millimeters thick. So this is one of the types of example questions you'll likely see on your homework. Cookware comes up pretty frequently since you have a pretty big temperature gradient across the metal of the cookware. You'll also commonly see examples involving the walls of houses. So this one will be the cookware example. I have a different sample later on for the wall of a house. So the information we're told here. We have, 1, we're told the material the pot is made of, copper. So we can tab back to the previous slide and find the rate of thermal conductivity for copper metal. So we have the K constant for the material we're looking at. We are told the temperature difference across this particular object. The pot itself, the physical pot, is placed on a stove eye. The hot stove eye is at 300 degrees Celsius, so that's going to be the hot side. Inside of the pot is ice-cold water, and ice-cold water is 0 degrees Celsius, so we do know that water's temperature. So the hot temperature on the bottom of the pot is 300 Celsius. The inside of the pot is 0 Celsius, so that's going to be our temperature gradient, our hot temperature and our cold temperature. We are told the diameter of the pot and the thickness of the pot. Now, its thickness is the L term in the formula. How thick the metal is the L term. So we have L. That's good. Admittedly, we were given millimeters for our thickness. We do need to convert that to meters before we use it. We were also told the diameter of the pot. This is useful information, but the formula doesn't call for diameter, it calls for surface area. Now, a pot, most pots that I've seen, at least, tend to have circular bottom sides. So, if the bottom of the pot is a circular with a diameter of 12 centimeters, we can use that diameter to find the flat surface area of that circle. So we're going to need to use our diameter to calculate surface area before we can continue, because our formula calls for area, not diameter. So I had to do a little bit of digging. I had to dig up the good old geometry formula for the area of a circle, because the flat part of the bottom is just a circle. Area of a circle is equal to pi times radius squared. Pi is going to be 3.14. Our diameter is 12 centimeters. That would make our radius 6 centimeters. For a brief refresher, if you haven't used these terms in a while, diameter refers to the entire width of a circle. Radius is only half the width. It's the distance from the center to the edge. So we would need to divide our diameter in half, and then we would have to square it as a part of this formula. I'd say the last trick to be aware of is I always recommend converting your units before you start using them in formulas, before you start multiplying them. Half of 12 centimeters is 6 centimeters, but if you were to plug 6 centimeters into this formula, you'd get an area out in centimeters squared. We want meters squared to be able to use this number correctly, so I converted 6 centimeters into meters first. 6 centimeters would be 0.06 meters. I converted that first before squaring it, and that would give me an area of 0.0113 meters squared. If you were to find it in centimeters squared, you'd get probably about 113, which again would be the wrong unit. We want meters squared for this. So I tend to do the converting on the front end to avoid having to do more complicated conversions on the tail end of the question instead. So with this little piece of math here off to the side done, we now have A, L, our temperature difference, and we know what it's made of. We have the K constant. So using our new formula, that's everything we need to find P, to find the power. So, looking back at the formula here, P equals Ka times temperature difference divided by L. Our K from the table is 397. The area that we just found is 0.0113. Our temperature difference is 300 minus 0. Since this is basically delta T, it's one temperature minus another to find the difference. Celsius is legal here. Just make sure that if you use Celsius or Kelvin, that the two units of the two temperatures match. And then lastly, L. We're going to divide by the L term. 2 millimeters is 0.002 meters. And that's every variable plugged in except for P. We can now solve for P. When I did this, please let me know if your math disagrees. I have a final answer of 673,494.6 watts. The metric unit for power is still watts, same as in Physics 1500, and 1 watt is defined as 1 joule of energy flowing per 1 second. So, this many watts, I'm just going to say as an example, 600,000 watts represents an energy flow of 600,000 joules every single second, which is a lot. That's very fast. And again, you kind of want the energy flow to be fast if you're trying to cook. You're trying to heat this water up to be able to use it for something. And again, this fast speed is facilitated by how thin the metal is, how big the temperature difference is, and the fact that we're using metal as opposed to, any other material. All those factors combined create this very high rate of thermal energy flow. Let me know how that feels so far. This is one kind of common type of example that one might expect to see on the homework and the test. Before we break, before we sort of end this thermal conductivity section, there is a slight twist on this formula that does come up from time to time, and I want to show it to you and describe it to you now while we're sort of on this train of thought. We tab back a second to look at the formula we were just using, P equals Ka times temperature difference over L. This particular formula only works when calculating the thermal energy flow through a single material. Notice again, the K, the A, the L all assume one specific object with certain... The puppy's growling at me, or whining at me, sorry. This formula assumes one object made out of one material with certain finite dimensions. Oh, hello. How are you doing? It cannot calculate an object that is made out of more than one material. I mentioned earlier double-paned windows, windows that have 2 panes of glass and air in the middle. You can't use this formula for that because the thermal energy passes through glass, then through air, then through glass again. So you could not use this to find the rate of thermal conduction for that entire window at once. You also couldn't really use it for the walls of your building, assuming that your walls are made out of more than one material. Usually some combination of wood, maybe brick, insulation material, and drywall. Those are all different materials. They all have different properties. So this one formula doesn't work for those composite situations. Some very smart people modified this formula to work for those composite situations. And of course, it has a different table of constants because all throughout this entire section, we've needed a new table every time we look at a new formula. So sorry, we can't reuse the old ones. This formula here on the bottom is the modified version that one uses when looking at the thermal conduction through a composite structure. Say again, we're looking at the rate of conduction through a wall of a building. Walls could have some layer of brick, some layer of wood, some layer of insulation, some layer of drywall, maybe some layer of paneling on the outside. All those different layers add different amounts of insulation to the wall. And so the formula was changed so that we could basically add all those layers together and look at them as one lump sum. So some very smart people took the original formula and they basically combined the K term and the L term together into one term. They took those two things and made one new constant out of them. And that new constant is this R down here in this modified version. This particular table is one that's used most often in the American construction industry. And since it was made and used by Americans, it's not in the metric system. These R values represent the thermal conductivity, the insulative properties of various thicknesses of different materials. Since the construction industry tends to work in certain standards of how thick things are and what they're made of, this table represents the R value, the insulative value for certain thicknesses of different things. So this table has entries for 1 inch of hardwood siding, 3 inches of brick, 1 inch of solid styrofoam. So if you wanted to try to figure out the thermal energy flow through a composite wall made out of a bunch of different materials, you'd want to determine what materials the wall is made out of, find the different R values here that represent those materials and how thick they are, and then in this modified formula here, instead of factoring K and L separately, you are going to add all of those different R's together to make one big new combined super R for whatever wall you're examining. So the modified formula is power equals surface area times the temperature difference divided by the sum of all the R values of all the different layers of the object you're examining. So the formula itself hasn't been changed that much. The same characteristics are still here. They've just been rearranged and sort of rebranded for a different context. In my own opinion, the most aggravating part of this tweak to the formula is the fact that since this was done by the American construction industry, the units were all changed to American metric units. Instead of meters, this formula uses feet and feet squared. Instead of Celsius or Kelvin, it uses degrees Fahrenheit. Instead of joules per hour, instead of joules per second, it uses a different unit for energy called British thermal units, and it uses hours instead of seconds. That is the most infuriating part. This is a different version of the formula for a different context, and so it was changed. The units being changed, I think, is the most dramatic part of it, the most frustrating part of it. Penny. No, Penny. I want to demonstrate this tweaked version real quick, just so that you have some context for it. Since this is used mostly for construction, let's actually use it in a construction context for a building. Hottest day of summer, 110 degrees Fahrenheit on the outside. Your home's walls are made of 4 inches of brick, 1 inch of fiberglass for insulation, and then a layer of drywall. Your walls are 10 feet tall by 20 feet wide, and the inside of the house is 70 degrees Fahrenheit. What is the rate of transfer of thermal energy through the wall of this house? So, if we want to use this modified version of the formula, A needs to be the area of the wall. We were told the walls are 10 feet by 20 feet, so that area would be 10 times 20, about 200 feet squared. Temperature difference, since this is a weird imperial American version of the formula, we're actually going to keep Fahrenheit this time, since our R values use Fahrenheit for their metric here instead of anything else. So outside the house is 110, inside the house is 70. Lastly is the sum R term. If I didn't mention it yet, this is the Greek letter sigma in front of the R. That represents summation, the sum of all the R's of all your different layers for your object. So our layers here are 4 inches of brick, 1 inch of fiberglass, and then a layer of drywall. I've shortened the chart here just to show those few things. So 4 inches of brick has an R value of 4, 1 inch of fiberglass has an R value of 4.35, and a standard drywall sheet that's half an inch thick has an R value of 0.45. Since those are all of our layers, we want to add all those R's together to become the total R for this composite wall. And so the sigma R down here becomes that summation, 4 plus 4.35 plus 0.45. And that's everything that we need in order to find the power through this particular wall. Multiply everything, we get an answer of about 909 British thermal units per hour. It is a weird unit, I'll admit. But 909 British thermal units per hour would be our answer here. And we could convert that into, a standard watts if we needed to. I already did convert it into watts. 1 BTU is equal to this many watts. So I converted that into watts, and that would tell us how many joules per second would transfer into and out of this particular wall. This way of using the formula won't come up often, but it does come up in the homework, and it's handy to understand how the composite materials work, because it does require a little bit of different thinking to, a material made, an object made out of just one material. So that is the end of the official Chapter 11 content. I did a lot of talking today, a lot of hand waving. So I'm going to call a break here. You guys can pause, go to the bathroom, get some water, relax your brains. And I recommend taking this information, going over your homework, getting started on the conduction problems there. I'll be here for the next hour if you jump back in with questions. Tomorrow's lecture, tomorrow's class call, we won't discuss anything new. Tomorrow's class call will be opportune time for you to, we can review any of the material from Chapter 11, go over any homework questions that you have or any issues you had working on it or the quiz. So tomorrow it will be review and going back over things and homework help. We won't cover any new material tomorrow. I would expect to begin Chapter 12 and the laws of thermodynamics on Wednesday. Does that sound... Let me know if you have any objections or questions to that. And I'll just wait a second. All right. Go ahead, take a break, look over the homework, let me know what you need as it comes up. I'll be here for the next hour. If I don't see you again today, come tomorrow with any questions or review stuff that you need or want. Also email me anytime. I'm rambling. We can go ahead and pause here, and if I don't see you again, have a nice day.